Presentation for this evening. Our presenter is a young lady who lives up in the Cleveland area, and she is a recent PhD graduate. And so she's now Dr. Collins, and her call sign is KD8OXT, and she is part of HAMSCI. And if you've never gone to the website, go to hamsci.org, HAMSCI.org for more information. And I'll let Kristina talk more about what she's going to talk about and all the fun things that she's doing with ham radio. And Kristina, over to you. Thank you for being here.
Thank you. Thank you very much. Can you guys hear me all right?
We need to turn up the volume, Corey.
All right. It may be on my end.
Got it up to 11, Kristina.
Okay, can you hear me?
No, we can, but you need an amplifier, please.
It's a little low
All
on
right,
Zoom.
let's see.
Yeah.
Getting some feedback on my end. Let me know if that's affecting
Keep going.
you.
Keep going. Keep going. Now we're starting to hear the hum. Come on, turn it up.
Okay. All right. How's that?
It's better, but you're like 5 and 5.
Let me get into my settings. I think that it's got, I think it's probably got sound turned way down. Zoom likes to do that for no reason. Okay. Turning up gain on my end. Can you hear me now? There we go. All right.
There we go.
Thank you, everyone. So I was checking my files. I have a passing familiarity with your club. I came by in person once 10 years ago, and we had a lovely time. We were there for a talk that Tim Gallagher was giving, so I really appreciate the warm welcome then as well as now, and just keep doing what you're doing. It's wonderful to see. So yeah, I'm here to give a brief report on our installation of a personal space weather station, which is a HAMSCI project at K3LR, and to talk a little bit about HAMSCI. So I'm going to keep it relatively brief and show you some of our various photos from the lovely trip that we had. I see that Amy is also here, which is wonderful. Hi, Amy. Here's the pile of everybody that we'd like to acknowledge. I'm sure I am missing a few. Much of this was brought to you by the National Science Foundation and viewers like you. Also, Amateur Radio Digital Communications, and of course, we want to acknowledge all of our volunteers and contributors in HAMSCI and the open source software projects we use and so forth. So, particularly NSF. All right, so for those who have not encountered it, HAMSCI is it's an unincorporated initiative. The center of it is at University of Scranton, where Nathaniel Fursell W2NAF is down in the left corner there. And the purpose of HAMSCI is to have an avenue for space scientists and amateur radio operators. There's a lot of overlap between those two groups to do things that are mutually beneficial to both communities. So there's always sort of this balance between two questions that we're asking ourselves. One is, what can amateur radio do to support space science investigations? And now that we're getting good at answering that question, we can finally get into the question of what can space science do to make amateur radio yet more interesting. The other thing that HAMSCI does, as you'll see in some of the following slides, is there's a lot of emphasis on college amateur radio club partnerships and talent development of, helping folks in the ham radio community to learn more about space science, and also bringing space scientists into the ham radio fold so that they can use amateur radio equipment as instrumentation and learn about the culture of amateur radio and become advocates for it in their scientific communities. So you can find information about it at hamsci.org. I'll be saying that phrase a lot. It's going to be in the lower left-hand corner of every slide. But I hope you'll consider joining our email reflector, because it's a wonderful bunch of people. There's some here, but this is a small cohort. This is, I think, just who happened to be at our Dayton booth like 5 years ago in that photo. I don't know exactly how many people we have, but there's a lot of people on the mailing list. So the flagship project of HAMSCI, and this again is supported by the National Science Foundation, is what we call the Personal Space Weather Station Network. And just like a regular weather station network, the Space Weather Station Network is a modular setup for data collection. So there's some interesting history here in terms of the amateur radio service. I think a lot of hams understand that amateur radio goes back to about the same time as the discovery of the ionosphere, right? Because the way you discover the ionosphere is you figure out that the waves you're sending out didn't go to space. They bounced and came back down to the ground. And that's how Marconi was able to talk across the Atlantic. So the transatlantic tests, the first proof that we could really conclusively get signals across the Atlantic on HF, was in a lot of ways the first ham radio contest, certainly the first major one. And so these are two things that have always been kind of connected up. Now, weather networks actually go back to radio communications in a somewhat similar way, in that they go back to the telegraph, and that's very bound up with radio. It's bound up, obviously, with, the lineage of Morse code and so forth. There was an understanding that pressure varied when weather events came through. And some people had figured out that you could chart pressure as you traveled across a distance, and had sort of this idea that if you could know what those points were pressure-wise, you'd be able to get maps. Ben Franklin famously characterized the Gulf Stream on a voyage to France this way. But it wasn't until we had the telegraph that you could have stations posted around the country and have them report back what weather conditions they were seeing. And that was how the National Weather Service got started. It was actually a citizen science project where the government would send people weather vanes and have them report back. So this is on the same basic model as that, except that it's amateur radio operators maintaining these radio stations. This is what one of the standard ones looks like these days. Again, just like weather stations, one might have a barometer and another might have an anemometer. They're modular. You might have different modules in different ones. And this is like the third or fourth revision of a personal space weather station, but they all contribute data to the same central database. The one that we installed at K3LR is like this. So the main parts of it, there's the GPS disciplined oscillator, which is a very important component because it lets us get precision timing quite inexpensively. Similarly, the single board computers are much cheaper than they used to be, so we can record data inexpensively. That's really why this approach is catching on. Those are our version of the telegraph, making our work possible. And then we have the software-defined radio, which is employed largely in detecting whisper spots, but also just binning all of the IQ data that it can, so that we can pick up interesting things. So I'm going to focus on the use that we've been doing for several years now of WWV as a signal of opportunity. I'm sure you've tuned into WWV on your HF radio, 2.5, 5, 10, 15, 20 megahertz, sometimes 25, depending on when you were listening. And we use WWV as a signal of opportunity. It's got a very, very precise carrier because it's run by NIST. And we use that to gather data about the ionosphere in order to look at propagation paths somewhat like the ones in these pictures, where the transmitter would be at the lower left-hand corner, and it sends a bunch of rays out into space. And somewhere in that fan of rays, there's one that's bouncing off of the ionosphere. And by bouncing, I mean refracting plus reflecting at such angles that it ends up landing in the receiver over here. This is a very approximate model, but we're going to stick with a simplified model for now. So this path on the globe here shows you WWV to Nathaniel Station, and I've got this little figure here now, which I'm going to kind of zoom in on. And this is a very simplified idea of what's going on with the ionosphere. So all models are wrong, but some are useful. We can get very far in pretending that the ionosphere is just simply a surface, and we can forget about refraction. We can pretend it's just reflecting off, right? So it's just moving up and down throughout the day. And it might move up and down in waves. And I'll show some examples of that here in a minute. But every day you do see the same basic trend that everything else sort of lands on top of. And that basic trend is that the sun rises, it creates photoionization in the ionosphere. You can imagine it as the ions sort of take up more space after photoionization. And so this sort of dotted line, what we call the virtual height of the ionosphere, moves down. And when it moves down, that path that already exists that's bouncing off of that point all the time, it's got these wave fronts, and the wave fronts contract. They get blue shifted in Doppler terms. This is electromagnetic Doppler, which is subtly distinct from acoustic Doppler, like when an ambulance is coming toward you and going away from you and you hear that pitch shift. But for our purposes, again, all models are wrong, but some are useful. You can think of it in those terms. So sun rises, virtual height decreases, those wavefronts get scrunched, and the received frequency over here at W8EDU at Case Western, or whatever station you have at K3LR, any of our receivers on the PSWS network, that received frequency ever so slightly increases because you're hitting more wavefronts in a given period of time. Nighttime comes, the process reverses. We're all familiar with being able to get further propagation paths on some HF bands when the nighttime comes around. That virtual height goes up, and then the process is backwards. So now the wavefronts get stretched out. The received frequency goes down ever so slightly. So remember, that carrier, when it starts out on the left side of the screen at WWV, that is always starting at 10.00000, 1 part in 10 to the 12th or 10 to the 16th accuracy megahertz. And that signal is going through distortion from the ionosphere, and then we are measuring that distortion. We actually use the same tools that contesters use who do the frequency measuring test. Our initial version of this was an adaptation of the FL Digi tools for that. So there's another really good example of the crossover between ham radio contesting activity and something that we can use as a science tool. It was adapted from those things. So this is the main signal that we're monitoring, is this carrier of WWV. So what kinds of events are we interested in? This is, again, that map from WWV to Nathaniel's station at W2NAF over here. And then we have also the Canadian time standard CHU, which is doing much the same thing. These two lines may look a bit familiar if you're into astronomy in the past couple of years. This is the annular eclipse in October 2023. And this is, of course, the total solar eclipse of April 2024. And so those create sort of a localized nighttime. So that day-night cycle that I just described, that'll happen in miniature when the eclipse comes through. So let's see, this is what that data looked like for the annular eclipse. You can see it's relatively homogeneous, and then there's this dawn spike. And then the eclipse creates this beautiful, fairly subtle S-curve. So first we get the nighttime effect, and then we get the daytime effect right there as it passes across that path from WWV to W2NAF. Here's another interesting example. This is the 8th of April, 2024, a little bit more dramatic. And again, WWV is on different frequencies. So 5 megahertz at Nathaniel's QTH, he just doesn't have much of a path at all during the day. There's a very subtle S-curve here. These dots mark where the eclipse took place. So we've got sunrise peak, sunrise peak, sunrise peak. And you also see that these lines are splitting into multiple lines. That's because there are multiple different paths that the rays are taking going from the transmitter to the receiver. So you may hear some of these effects in your ham radio. We're interested in gathering those data so that we can use it to make our models of the ionosphere better. And then you can see the same basic S-curve, just in different ways depending on what frequency you're on. Similarly, CHU, they don't have as cool frequencies as we do here in America. They've got 3.33, 7.85, none of those round numbers, but they also have a decent range of frequencies to measure 3 different bands. And once again, we see that S-curve of tiny nighttime, tiny daytime. We happened to get very lucky in April. We had a very geophysically quiet day, except for this eclipse. And eclipses are a wonderful thing because they're really the closest you get to a controlled experiment in space science, but you only get one shot at gathering the data. So if you have just one station, there's some interesting things that you can do with this. And this is one of our older stations. All this is doing is measuring the shift of that carrier and not looking at anything happening at the sidebands at all. So you wouldn't get any of that extra interesting spectrogram stuff. You'll just get like the estimation of the carrier. But even with this, we can get some very interesting results. So these are daily plots on the left. And these little like, wobbly bits that you see are related to traveling ionospheric disturbances, which can be created by a lot of different events. But on the right, this is multiple years worth of data. So this goes from 2020 through to 2022. And each line of pixels from 0 to 24, that's 24 hours of data. So we go through one day, and if it's more red shifted, so a lower frequency shift, then it'll be more red, and if it's higher, it'll be blue. I have an alternative color map for this. If anybody's colorblind, let me know and I can pull that one up. But we use red-blue because it's hard to get a good, what's the word I'm looking for? A good color map that works in both directions is very challenging to make accessible. But you can see at least the lines here that represent the changing length of day. So you can pick out where the solstice is, where the equinox is. So it's one day of data is one line of pixels. Next day of data is the next line of pixels, and so on. So here's the blue shift from that daily sunrise and the red shift from that daily sunset. And then you can kind of pick out things like, oh, well, it looks like there's more activity sort of for this month-long period here, or this period here, things like that. Down here, we have the amplitude plots for the same sets of data. And this particular thing that you see here, where the whole thing just kind of like pops up the received power scale, this is the moment that John swapped out his antenna. That's all that's happening there. So that's what one station's data looks like. But this really gets interesting when we have access to many stations. And one thing that's worthwhile about the ionosphere as an object of measurement is that it is in between terrestrial weather and space weather. So it's affected by events that occur above it and below it. I have one example of each here. On the left, this is an X-class solar flare from 2021. And that's panel A, right? So that's you can see where the solar flare occurs at this point. And in panel B, there's this, we call it a Doppler flash, just before that, where you can see the stations all had this sudden jump in received frequency that goes away, coincided with an RF blackout in panel C. But the interesting thing about this, if you look at the color map here, is that this is a smooth gradient of longitude. So actually, by having multiple stations, we can figure out exactly where that Doppler flash occurred because we know the points where the WWV path was to each of those stations. And so that's a subject of some current research that we're doing. We're waiting back to hear if we're able to get some funding to pursue that question further. I should also point out, as long as we're on these figures, that later in the day, you can see this is the X1, that's a bigger flare. C4.9, that's a somewhat smaller flare. It gets a similar effect to a lesser degree. So we get this fantastic little solar flare detector. Every day I log on to my email. I get the daily plots in my email. This is what I do instead of Wordle. I look through the peaks and try to guess what kinds of solar flares we had that day. So that's an event from above that can be measured with equipment in your backyard that's, a couple $100, and most of that is the GPS disciplined oscillator. And you can also measure that just by measuring Doppler with your ham radio, the way that you do with frequency measuring test tools and FL-Digi and so forth. So then another example of an interesting event, I talked about traveling ionospheric disturbances earlier. You may remember the let's see, this was January 2022, the Tonga eruption volcano, the Hunga Tonga Hapai volcano exploded, and it's an uninhabited atoll, but it was just underwater enough, and the numbers all worked out that it ejected this water really, really far up into the stratosphere and just sort of like, punched the atmosphere in this very forceful way, such that there was a wave called a Lamb wave, went all the way around the planet, reflected on itself, came back several times. And so anybody who was measuring anything saw some perturbation in their data from this. And scientists get very excited about that sort of thing because, you rarely get to see a true calibration event in Earth science. So this was the data that we had. Here's where the eruption took place, and here's where that Lamb wave crossed over for North America, right around there. And then the following day, you can also see that reflection. So here's some NASA satellite imagery that's been color shifted to really highlight where the wave is in the atmosphere. And then this is a simulation of where the wave is. There's a little bit of kind of fun discourse among scientists as to exactly what time the eruption took place based on these measurements, but it was a pretty big, obvious event. So the level of disagreement is like, I think it was 1 second earlier than the other guy. So that's a fun thing that we've observed. And then one more look at the eclipses. This is the New England Grape Group, as they call themselves, but a lot of these are in other places as well. We've got Harvard, Massachusetts, Cleveland, Ohio, Hoover, Alabama, Florida, Kentucky, Tennessee, New Hampshire, North Carolina. Each of these lines is a different station measuring WWV on 10 megahertz. You can see that their sunrise peaks are a little bit offset, but again, there's that beautiful April 8th, 2024 eclipse S-curve. And it's really almost as pronounced for most of these as the dawn was, in some cases more so. So there's lots of interesting data to be collected about the ionosphere in this way. And there's about 50 of these stations or more that are live right now collecting this. So that's the sort of thing that we're looking to collect. I'm not going to go into depth on this eye chart on the right here, but suffice it to say that there are several different instruments for the Personal Space Weather Station. Some of them we are producing ourselves, and they're going to be a fairly limited run, and we're going to strategically place them. Other ones we're making the information on how to build your own publicly available, and you can build your own and you can connect it up to the network. So with that, let's talk about the K3LR installation that we did in August of this year. This was an absolutely fantastic time. Here is Nathaniel wearing his shirt that says, "The world would be a better place if more people studied the ionosphere," which I hope is still for sale at Dayton Hamvention because I want one. And the general tasks that we set forth for ourselves as a group for this was people from Case Western, where I come from, with Cleveland, Whiskey 8 Echo Delta Uniform, hi. And then also the University of Scranton's Amateur Radio Club and General Research Group. The first goal was the installation of a ground magnetometer and the Whisper Demon RX888 wideband SDR. We really need to come up with a catchier name for that, but it's the software-defined radio that's doing all those things that I showed you a couple slides ago, and an active antenna. So I'll show you where we put those at K3LR's site. And the second goal was for students from both of the schools to talk to each other and to spend some time doing ham radio and talking about, the connections between ham radio and space physics, and then also just to get to hang out with Tim and Amy and the whole crew there and have a wonderful time at the station, doing some ham radio and working on this project together. And so here's a group photo from that, and I've got some other photos from the various parts of the trip. So first, just to get situated as to where the station is, I'll show you some of that. Here's the house. Here's those glorious antennas that you can see from the highway over here. Here's the various bunks for high-profile contesters of the world. This little red circle here encloses what's known as the Mouse House, which is this red outbuilding on the left of the picture on the right, and that is now dedicated to the Personal Space Weather Station. So when we went there for the first trip, we initially set things up in the building here, ran cables. Now all of the systems have been moved into this building. So here's Owen and Bob bearing the magnetometer, and you can see that the rest of us are over here supervising. And that was, that's a few feet deep. I can give a paper for anybody who's interested in building one of their own. There's a peer-reviewed paper in that, in a journal paper that explains how it works, how it's built, how you can build your own, and how to run it. We, of course, did a tour of the towers. We got to look inside all the boxes, which is a lot of fun. Talk about all of the cable setups, the grounding systems, the different types of antennas. Although I still really want to make a map so I can keep them all straight. I don't know how you guys remember. And of course, the this particularly gorgeous. This is the 40-meter setup. One of the things that came out of this that was also really great was we did a sort of impromptu ham-size salon, as I called it. Tim let us use his big screen TV to give some short presentations. I talked a little about visualization, and these are the University of Scranton students talking about, on the left here, we have Owen talking about whisper spots that were identified from K3LR's receiver just in the time that we'd had it set up. And then on the right, we have some other students talking about their work on the Gannon storm, which was a large geomagnetic storm from, I want to say it was last May, which hopefully you got a chance to see some of the auroras because it pushed the auroral oval all the way down into Mexico. And that's named for Jen Gannon, who was one of our colleagues in space science through AGU, who passed away at a young age a few years back. So operating the station, this was, of course, a highlight. Here is Tim giving us the tour, and he's got this fantastic wallpaper of all of the contesting awards. This is Gary and Rachel of Case Western. Here's some of the Scranton students. There's Kate right there. And this was a bucket list item for all of us. This was a lot of fun. And so, we were like, okay, well, we have to make sure that there's not too much QRM for the station, and indeed there wasn't. Everything worked really swimmingly. And then one thing I really want to make a point of here is thank you for all the food and the hospitality and the hosting. That was really absolutely fantastic. And this is a quote from one of my favorite book by Virginia Woolf, A Room of One's Own. I'm sure you've heard of it, but probably haven't had a chance to read it. It's a magnificent book. But one of the things that she talks about in it is this idea that novelists, whenever they tell you about a party, they want you to think the party was interesting because of something someone said, and they skip over the food. And she's like, no, I'm going to talk about the food because the food is very important for real, true intellectual exchange. And so that was absolutely provided by K3LR, and it was greatly appreciated. We really had a wonderful time. All right, so then there were a couple of tasks yet to do. Tim made some renovations to the mouse house to make it very hospitable for the whole setup. So this is what it looks like today. We have one of those collapsible tables, and it's nice because you can just drill into it to mount things. And there's all of those things were moved from that house I pointed to earlier into the outbuilding. Gary buried this cable. I was on a Zoom meeting. I'm afraid I was no help at all. He did a really good job. And so the cable is now buried. This is, again, the magnetometer, and this is the active antenna here. And so this is the whole setup. We got some photos. We're going to use this for our, going to put together a hardware paper describing how these systems are set up. I think this one will probably be our exemplar for that. And we did another little ham-sized salon. Here's a couple photos of Gary presenting some information on the ionosphere, and this generally to students from Grove City College who came by for an antenna tour as well. So that was also fantastic. If you'd like to check out the station yourself, you can go to this site, http://vpnhamsci.org 46006/radio.html. So I'll give people a second to jot that down. And if you'd like to look at data from any of the PSWS stations, you can go to PSWS for Personal Space Weather Station, psws.hamsci.org, and you can see these, this is a bit of an older map, but you can see all of the dots for different stations, the status of whether they're registered or currently operating, and you can go in, find data from different dates, you can export CSVs, you can export plots. We are currently in the process of designing how exactly the API will work, having, being able to pull all of this stuff with Python so that if I want to look at it as a scientist, I can get to the point where I'm just like pushing one button and being able to see all of the data for a given period of time. The goal is to have this all come out smoothly, as a map, just like the National Weather Service. And I think that once we get to that point, we'll be able to see weather. We'll be able to essentially see space weather. That's the goal of the network. And hopefully that will then also be of use for the amateur radio community to be able to figure out where their signals might be going. So here's just a list of digital object identifiers. These are all essentially links. You just put doi.org and then put these after it. And I can drop these into the chat if anybody's interested, of different articles that sort of summarize the work that we've done with the Personal Space Weather Station to date. I can also give you a link to the HamSci newsletters. We have a regular quarterly newsletter. It's managed largely by volunteers. It's a fantastic piece of literature. Great graphic design by the University of Scranton graphic design department. And it has interviews and summaries of literature. I've recently been lobbying to put in a crossword puzzle. We'll see if that happens. Photos, updates, just general information about what the community's been up to. That comes out 2, 3, 4 times a year. So we've got one of those coming out pretty soon. Finally, if you'd like to get involved with HamSci, just go to hamsci.org. There's this nice big blue button right here to join the mailing list. And don't be shy. It's a wonderfully welcoming group of hams and space scientists who are interested in sharing what they know about their areas of interest. And then I'll, there we go. And then in closing, here's a shot of our gorgeous new towers on the roof of the Glennon building here at W80DU. And if you're ever coming up to Cleveland for any reason, please drop me a line. We'd love to give you a tour and spend some time on the radio. And with that, I'll just ask if anyone has any questions. Thanks.
Very nice
Hey,
presentation,
Kristina.
Kristina.
I have a question, Tim.
Yes, go ahead.
I want to ask Kristina. Hi, Kristina. I just wanted to ask, is our space weather station beating the other space weather stations, or, is it louder than the others? Just wondering.
That's a good question. So it's listening. It's not an active one. One of the exciting things about the network is that we do have we're starting to put in our own active stations, our own stations that transmit. So if you're listening, right? Because right now we've got WWV and that's one beacon. So if I have one beacon on my map, then I have one receiving station. I know where sort of the midpoint between those is, right? So that's one point, that's one pixel in my picture of the ionosphere. If I have a second station, I get 2 pixels, right? Now, if I keep adding receivers, that stays with whatever the number n of receivers I have n pixels in the picture. But if I add another transmitter, right, I get a bunch more. And so we are planning to get some active stations in, and that will immediately and vastly increase the amount of data that we can get out of this network. So I'm very excited for that in the coming years. As far as how this particular station is standing up to the others, I'd say that it is it's absolutely one of the prettiest. That's why it's going in the paper. But I think that there's been some things about setting the gain. I think that there was a thing in the mailing list about the gain being a bit low, and I'm embarrassed that I don't know the details on that. But it's on the HamSci email reflector if you want to check it out. I would say it's acquitting itself very well, and you can see how many whisper spots it has. That might be a good way for them to compete. So, but the gamification is at the core of contesting. So it's actually not a bad idea to pit them against each other in a friendly competition a little bit.
Oh, yeah. Thank you so much.
Thank you.
Thank you, Amy. Anything else for Kristina? Again, you are the youngest version of Dr. Firehose now, because it's like drinking from a fire hose when you talk. And we really appreciate you coming virtually via Zoom to the Mercer County Amateur Radio Club. How about a nice round of applause for Kristina?
Thank you very much. Absolute pleasure.
Okay, Kristina, go out and, investigate and design and invent something, all right?
We'll keep you posted.
Leave your mark. Thank you for coming.
All right. 7-3, everybody.
73. All right, we'll be gathering up at La Isla, and we'll see you here next